Today's lesson is about the composition of functions, and that is a brand new phrase. So instead of finding f at 2, what would happen if I wanted you to find f at, and in here I put a whole other function. So f at g at x. Combining two functions in this way is called composition. The new function is called the composite of f at x and g at x and is written like this. So you thought you knew all the operation symbols, add, subtract, multiply, divide. Well, here's a new one for you. It's like an open circle. And it's showing a composition, it's showing this new kind of thing. Now, it's kind of like saying, when you were 3 years old, how old was your older sister? And then let's say she was 8. Okay, and when she was 8, how old was your parent? So it's taking one number from one relationship and putting it into a different relationship. Here we have x and y's. These are y's, but we're calling them g at x. So we've got one set of independent variables here. We could graph them, some coordinates. And here's another one. So we want to take two different functions, g at x and f at x, and we want to compose them. We want to put them together. So what we do first is we go to our first function, which is the g at x function, and I'm just going to take all these values here and I'm going to put them in this column right here. So that's my first step. So you're just going to rewrite all of these numbers into here. So I'm taking some values from my first set of relationships. So when x was -1, g at x was 2.5. Okay, now when g at x was 2.5, what's f at x? Or for equivalently for any of these here. Let's start with this one here. When x was 0, g at x was 3. Okay. Now we go to the other function and we change this 3 now when we look for it in this column. When x was 0, g at x was 3. Move it over. This becomes our 3. This is like our g at x here. When that becomes 3, what's f at x? Well, that was a 0. So over here beside the 3, I put a 0. Now I skipped the 2.5 and I'll come back to it. I'll tell you why in a minute. Let's go down to this one here. Okay, so starting over here. When x was 2, g at x was 0. So I go up here to find the matching number. Now I'm taking the answer from one function, 0, and I'm making it the input of my new function. 0 now is my new input, and what is my output here? In this case, it's a 3. So that's going to go right here. So those were kind of the easy ones, actually. Now I'm going to look at that harder one, that 2.5 at the top. When I go back to my first coordinate here, when x was -1, g at x was 2.5. Now I have to look over here in this column for a 2.5. Well, there isn't one. There's no 2.5 listed in all of these x values. So I don't know what my output would be when I put in an input of 2.5. So all I can put here is undefined. I don't have enough information for that. And if you look at the question here, it says we've got discrete data. And discrete data means we only have some values to work with. I don't have, this isn't I'm not given an equation. I don't know. I can't go ahead and find out. I can't find f at 2.5 by subbing it into anything. All I have is to look at some tables, and I don't have that. So 2.5 is undefined. Let's try 2. When g at x is -2, when g at x is -2, what is f at x? Here's f at x. What is f at x when we switch our input to a -2? Well, again, we don't have that, so that's also going to get a u for undefined. Let's go down to the 1. So remember, originally we took these g at x values and we just rewrote them. One of them was a 1, and for 1 we do have a match right here, so I can put a 2 there. And last one is -3. I look in my f at x values for an x value of -3. I don't have one, so this one's undefined as well. So this is kind of bizarre and confusing. It's going to make more sense as we actually have some equations that we can sub into and we don't have these undefined values, because we can actually get some answers. The composition of two functions exists, as we just saw, only where the range of the first function overlaps or is contained in the domain of the second. In other words, the domain of the composite function is the set of all x values. So remember our first table? X was in the domain of G, so we had all our x values there. And then the answer that we got from the first pair of our table, we had an x and we had a y. That y value had to be in the domain of F, and if not, it was undefined. So it's a little bit more of a confusing domain here. So let's talk about that. We're going to solve algebraically. We've got an f at x, we've got a g at x. We've got equations this time. Great. I don't have to rely on a table. I don't have to rely on discrete data and just try to find numbers that match up. So first of all, I'm going to write f at g at x. Let's start with, actually, I'm going to start with f at x here. F at x is, looking at the equation that I was given, is x squared minus x. If I were looking for f at 2, what would I do? I would put a 2 in everywhere there is an x, always substitute using brackets. But I'm not finding f at 2, I'm finding f at g at x. That's what this is right here. So everywhere, instead of everywhere that there was a 2, I'm going to have to put a g at x in all those spots. That's going to have to be a g at x. So let me write that underneath where it looks a little more sensible. F at, and then I'll change colors here, f at g at x is equal to, so I'm subbing in up here. I'm going to have g at x squared minus g at x. So I'm just subbing in the notation right now. That's what f at g at x means. Remember, if it was f at 2, all of those light blue things would all be 2's, but it's not. It's f at g at x. So that's equal to, what is g at x? Well, g at x is right here. That's what g at x is. So g at x squared is going to be, g at x is 4x plus 1. 1, and then I've got to square that, minus, again, g at x is 4x plus 1. So I'm doing the same thing that you've done since grade 11, which is to use substitute into function notation. What is 4x plus 1 squared? Well, if you can't do that in your head, then you're going to have to write out 4x plus 1 twice. And then, sorry, that's not squared, whoops. And then this negative sign comes in here. Negative 4x minus 1. And binomial expansion here is going to give me 16x squared plus 8x plus 1 minus 4x minus 1. And we collect all of our like terms. X squareds go first. There's 16x squared. And then our x's, we're going down by degrees each time, so this will be a 4x. And then our constants, well, they're gone. We had a plus 1 and a minus 1. So that is the equation of f at g at x. It's the composition of f and g. How about if we write it the other way? Part B says g at f at x. So let me start first by writing out what g at x is. G at x is 4x minus 1. But instead of subbing in a 2 for the x here, instead of putting a 2 there or a 2 there, I need to sub in, whoops, f at x. So I'm going to find g at, this time, f at x. F at x. Oh, messing up my colors there. There's an f at x. Equals 4. Now instead of subbing in a 2 here, remember, I'm subbing in f at x. And my constant is just minus 1. So what is f at x? Back up here, f at x is, let me get a red pen. This is f at x right here. So I'm going to sub that in here. And I'll have 4 times f at x is x squared minus x minus 1. Distributing in 4x squared minus 4x minus 1. Plus 1, plus 1, plus 1, plus 1, sorry. So that is our function g at f at x. So they're different, and that's kind of why I did this example, to point out to you that they're not the same thing. So f with subbing in a g at x is not the same as starting off as taking g and then subbing into it f at x. Those are not the same thing. So you do have to do them in the exact order that it's written out for you in the question. Well, let's try an easier one, one with a number. F at g at 1. Okay, so there's a couple of ways to do this. Let's look at g at 1 first. Let's work with the inside of the bracket. So I want to find out what f at g at 1 is. So we go up to our equation. Here's g. F at g at 1 is going to be f at 4 times 1 plus 1. So that's f at 5. So I could have also done that separately or done that in my head, g at 1. I could probably have done g at 1 in my head, right? I didn't really need to show the work, but that's okay. So we do g at 1 and we figure out g at 1 is equal to 5. Now that means I'm looking for f at 5. So I go up to my f function and I substitute in a 5 with brackets because it's x squared minus x, 5 squared minus 5. 25 minus 5 is 20. So that would be a point on our new function. Our new function would have the point 120 on it. When we subbed in a 1, we got a 20. That would be on our new function. So I would encourage you to look at these compositions on Desmos, type in these new functions and see if there's restrictions on the domain or the range. But we're going to actually try one to calculate domain and range ourselves. Example 3, determine the domain and range as promised of a composite function composed of g at x. Here's f at x, here's g at x. All right, here is the graphs. I tried to kind of color code them. This is f at x, it's just a line, 3x minus 2, right? Y-intercept of -2, slope of 3, that's this line right here. Then we've got cos, that's in blue. So we know what the domain and range of each of them are, because these are grade 11 functions, we know those. But what is the domain once we compose the function? So let's look at what f of g at x is equal to. F of g at x can also be written, and usually it makes more sense actually to write it like this, putting one kind of inside the other. So that's f at, now I'm going to look at the inside first. What is g at x? Well, that's cos x. So let me just change that to cos x. Okay. Now what is f at cos x? Well, here's f. Everywhere I have an x, I'm going to have to replace that with a cos x. So f at cos x is 3 times cos x minus 2. Okay. Looking at that equation, we can graph that. That's just the parent wave for cosine. The only change to it is amplitude is 3, so we have a vertical stretch of 3. And we have a c value of -2. So my equation of the axis is now down at -2, which I can barely read this, but I think it's here. So let's just put in a dotted line for the equation of the axis. And then I have to have an amplitude of 3. So this is going to come down from a maximum at 1. From a maximum at 1, that would be bringing us up to a maximum at 3, but then we have to drop it down 2. So our maximum's back there. Let's look at a minimum. We would have a minimum normally occurs at -1 on the cos wave. We stretch it down by a factor of 3. That's going to take it to a stretch of It's not really on the graph here, but a negative 3. It's going to go down here at that point. And then we're dropping it another 2. So we're dropping it another 2. It's coming down here to a negative. So this is really not fitting on my graph at all. It's not asking me to graph it, but I like to have the graph to see how things are changing. My domain, let's start with the domain first. This graph, of course, is not a difficult one to know the domain for. Domain is x's element of real numbers. X is an element of real numbers. It's just a cos wave with a few little transformations. How about its range? Now that's what I just talked about. What's its range? So remember, the range is always written, well, you can use y, or you can use, in this case, would be f of g at x. Y is a little easier. Y is an element of real numbers such that, and it's always like this: the minimum less than or equal to y less than or equal to the maximum. That's how we write the range. You can calculate that by taking the equation of the axis, subtracting the amplitude, and then the equation of the axis plus the amplitude, or the a value, but a positive, so an amplitude. So in this case, that is going to be, let me erase the words minimum and maximum. Okay. That's going to be a negative 5. That's our low point, and our high point is 1. So that would be, if I graphed it, I would be coming down like this, right? That's the range of our new function. So even though we put two different functions together, we put a line together with a sinusoidal, the equation was still one that we could recognize, and we still know how to graph, and we can still get the domain and range. So let's take a look at example 4. It's the opposite. We're going to decompose a composition of function. So we've had two functions that have already been composed together, and they made h at x. And this was the answer. G at x subbed into f gave us h at x. So what you have to do is come up with two functions, f and g, that would result in h at x. And there's a couple of different answers for this. So our g at x is our kind of our inner function here. So we've got, let's say we let g at x equal, so let's pick just 2x cubed plus 1. Let's say that's g at x. Then what would this is the inner function here. This is the kind of the inside part. So then what would the outer part be? What would I be doing to that function? What am I going to do to this so that I can end up with that? Well, that one's pretty straightforward. I just need to put it all to the power of 5. So in that case, my equation would be f at x is equal to x to the power of 5. There's other ways to write it too. So what we've got here is f of g at x is equal to, well, or we can write it the other way, f of g at x, oops, too many brackets, f of g at x, and that is f at 2x cubed plus 1. So that gives us our h at x, which is 2x cubed plus 1 to the power of 5. So that's h at x. The question was asking us to find two functions that would result in h at x. There are other solutions. Can you see another one? What if g at x were x cubed? And could you finish that one? Press pause and think about that for a minute. Did you come up with something? So we're looking now at f at gx, but that being an x cubed. How could I get 2x cubed plus 1 to the power of 5 out of that? That would work if f at x were just 2x plus 1 to the power of 5. Because once I take this x cubed and sub it in here, then I would have hx. So that's a little more challenging to think in the opposite direction that we're used to thinking. but there's more than one answer for that. The last thing we want to talk about with composite functions are inverses. So here's a line. F of x is just a line. We want to find its inverse. Okay, and here's visually what that is. 3x plus 1. Would that be the black line or the kind of burgundy line here? Well, we have to have a y-intercept of 1 and a slope of 3. So that's the black one here. Y-intercept of 1 and a slope of 3. So here's f of x. Remember what an inverse means. It means that when you take the line y equals x, that's your line of reflection. When you reflect your original function through that line, you'll get your inverse. So that's what our inverse is going to look like. But let's find the equation of the inverse here. So the equation will be, remember how to find an inverse. First thing I'm going to do is write the equation with a y. Y equals 3x plus 1. And I'm going to switch x and y. X equals 3y plus 1. Now I need to isolate y. So I'm going to subtract 1 from both sides. And then divide both sides by 3. And that is y inverse. I can also write that separately. I could write it as x over 3 minus 1/3. That's the same thing. That's also y inverse, or it is a function because it's a line, so I can use function notation here. F inverse at x. That's the same thing. So there's my inverse equation. Now looking at part B. Part B, now we're going to do some composites. Of course we're going to do some composites. I'm going to rewrite that in the form that I kind of like to look at it a bit better, which is like this with one function inside the other one. These are equal. So f at, what is f inverse at x? Well, I just found that right here. Here's f inverse at x. So I'm going to sub that in, whichever one I like better. I'll take the top one, x minus 1 over 3. That's my f inverse equation. Now I have to sub that into f, and here's f. Everywhere that I had an x, I have to replace with this stuff that's in the bracket. So 3 x minus 1 over 3 plus 1. That is, these cancel out, and I have x minus 1 plus 1. Well, that's nice. I just get x. So that's what the function composed of its inverse is. Now remember on one of the earlier slides I told you that composing f at g at x is not the same as g at f at x. You have to do them separately. You can't just rearrange them. So that's what I have here. I have one equation, I have one composition done one way, the other done the other way. I can't just assume they're the same. So let's work it out. I'm going to rewrite it first as f inverse at f at x. So inside the bracket, I'm going to sub in what is f at x. That's what I'm going to put in there. And although I scribbled all over it, let me erase that. F at x is 3x plus 1. Okay, that's substitution. Now I have to go to my f inverse, which again is down here. I have to go to that equation or this equation and sub in for the x. So instead of this x here on the left, I'm going to put in 3x plus 1. I have 3x plus 1 in for that single x in the numerator. Subtract 1 over 3. That is 3x plus 1. Whoops. Plus 1. I think I've done that twice today. Switched minus for plus. Okay, plus 1 minus 1 over 3. These are gone. We have 3x over 3, which is x. Well, I did get the same thing, and I just told you that when you substitute in one way, it's not the same as substituting in the other way. Oh, except for any function f, its inverse, whether we compose it one way or the other, it will always equal x. It's always going to be that. It's always going to give us the line of reflection. This is the line y equals x. So when we take an inverse, so if you get a question like this in your homework and it's a totally different question, it says find h at h inverse at x. Well, you don't have to spend all day doing that. The answer is x. So that is the only time where that happens. So let me just label all these here. The first, this on the graph, this was our new one here. This was our f inverse at x. And our original was the first line there, f of x. And then when we compose one and the other, we get the line of reflection. That's the answer for an inverse and its original function being composed together. That's the end of the composition of functions. So as always, do some questions of practice, try it yourself, and let me know if you have any questions.